So thank you very much for, first of all, for your invitation and also for the kind introduction. So first, a few words about simulating or emulating quantum computers. So in our opinion, it's very important to have these theoretical tools to simulate quantum computers in order to validate the designs of physically realizable quantum computers. And on the right, I have indicated a selection. There are, in the meantime, quite a lot of these devices. The simulation is also important to be able to investigate the implementation and the performance of quantum algorithms on these real devices. Then, if we can implement or simulate the implementation of such algorithms, we can also come to the design of use cases. And then I will also show an example of this in my talk. It also brings something if you're investigating quantum classical hybrid computation. So, but let me first say a few words about simulating a gate-based quantum computer, and then we consider the pen and paper version, which means that we simulate an ideal version of a gate-based quantum computer. No effects from the environment, no effects of temperature, and also no effect of leakage between the qubit levels. So as you all know, if you have a system with 1 qubit, then the wave function of this quantum system can be written as this superposition, where the amplitudes A0 and A1 are complex numbers which satisfy this condition here. We can then extend this to a system with n spin 1/2 particle, which describes an n qubit quantum computer, and then we have this wave function here. So this can be represented as a vector of length 2 to the power n, and this vector contains then all these complex amplitudes A. Now, a quantum algorithm on this gate-based quantum computer is nothing else than a sequence of quantum gates. And these gates are described by unitary sparse matrices. And this sequence then changes the state of the quantum processor. Now one can ask the question, where does the power of this pen and paper or this ideal gate-based quantum computer is coming from? If we have an operation of such a quantum computer, then this is nothing else than multiplying the wave function that describes the state of the quantum computer with a unitary matrix. And this operation, it's believed that, and it's without any empirical evidence, that nature knows how to do this operation in one step. Now, if we make this belief, then we also have to believe in a many-world interpretation. Now, if we have this belief, then it follows also that this ideal quantum computer is a superb parallel computer that can multiply a 2 to the power n times 2 to the power n matrix with a 2 to the power n vector in only one step. So this would mean that in theory, we see an exponential speedup because we perform then, instead of 2 to the power 2n operation, just one operation. And we see this speedup for all algorithms that can exploit this type of parallelism. And unfortunately, it is hard to find such algorithms. So the most well-known is Shor's number factoring algorithm. So that's in theory. In practice, if we have a quantum computer that did something, we also have to find out what the outcome is. And therefore, we have to measure. And it's exactly this measurement that might destroy the parallelism. And I will here shortly indicate why. So the output of the pen and paper quantum computer can be written as another state psi prime, which is just the result of this unitary operation operating on the state psi. So this means that we know all to the 2 to the power n complex amplitudes, and from this we can calculate all probabilities. Now, if we have a real gate-based quantum computer, then we have to perform this measurement. And in each measurement, every qubit is read out, and then you get a value 0 or 1, and this for each qubit. So each measurement, we could say, returns one of the 2 to the power n basis states. Now, if we then want to get information about these probabilities, then we have to perform many measurements. And the question is, how many times do we have to measure? Now, if we assume that each of these amplitudes would be different from 0, then we need 2 to the power n times a certain amount of samples, and this is to get good statistical information. Measurements are required. And then you can already see this is exponentially growing. So if they are all different from 0, our parallelism that we had in the calculation disappears. Now, the advantage of Shor's algorithm, and this is very important in this particular case, is that only a small fraction of the amplitudes is different from 0. So it's exactly this type of algorithms we have to look for. Now, I will say something about simulating such pen and paper quantum computers. So in this period of 10 years between 2007 and 2017, we developed the Jülich Universal Quantum Computer Simulator. And I make here a difference between different versions. So this is what we call the E version. It's the exact version in which we represent the n qubits quantum computer by its wave function, which is a superposition of 2 to the power n basis states. And each of the quantum states is represented by 16 bytes. So if we do this, then for n qubits, we need 2 to the power n plus 4 bytes of memory. And here you see what this means in practice. So for 46 qubits, we would need 1 petabyte of memory. Then on the right, you see some results for the normalized elapsed time per operation as a function of the number of qubits for an algorithm that performs an Hadamard on each qubit. So we then end up with a product state. And then you see several dates here. So in 2007, we simulated 36 qubits. Then in 2010, we had a world record on the Blue Gene machine. It was a Blue Gene P, which was installed at the Jülich Supercomputing Center. Then in 2012, we had the Blue Gene Q. And then we had the world record of simulating 43 qubits. And then in 2017, we had another world record in simulating 45 qubits, as well on the K computer as on the Sunway Tachylite. And from the plot that I have shown, you can see that we can say that for up to these 45 qubits, these supercomputers somehow beat the exponential growth. But we are, of course, bounded by the memory. Then in the period of 2018, 2019, we have set a few other world records. And this we could do by making an approximate version of chunks in which we represent the quantum state with only 2 bytes. So then we only needed 2 to the n plus 1 bytes for as memory consumption. So in that case, we could simulate, so to speak, 49 qubits if we would have had a memory of 1 petabyte. So, and here you see on the right that then we could simulate 48 qubits on the K computer and on the Sunday Tahilite. And in this case, we have simulated an algorithm that was performing a C0 operation on each subsequent pair of qubits, which in this case resulted in an entangled state. I must say, in many cases, at least for these simple algorithms, we don't see a real difference in outcome between this approximate version and the exact version of the code. So how does this simulator manage dealing with all these complex numbers? So for this, we, of course, have to distribute the quantum state over multiple nodes. And I give you here one example for 40 qubits. 40 qubits means that we have 16, or we need 16 terabytes to represent these complex numbers. And in this particular case, we say, okay, we take 64 gigabytes per node, and this for 256 nodes. So this is then the computer on which we calculate. And for MPI rank 0, we have this vector here. For MPI rank number 255, we have this vector here. So we have 8 global qubits. This is this 2 to the power 8. 256, and we have 32 local qubits. Then recently we made a GPU version of chunks, the G version, and in this case we distribute then the quantum state over multiple GPUs, and in this case we considered the NVIDIA A100 GPUs, which have 40 gigabytes per GPU. Although we can do it differently, I take again the case with 40 qubits. And in this case, we distribute it such that we have 16 gigabytes per GPU. And we consider this 4 times 256 GPUs. So this is now our computer, in which we have the nodes, and each node has score of these GPUs. Now, this results in the fact that now we can have 8 plus 2, meaning 10 global qubits, and we have 30 local qubits. And the MPI communication scheme that we use in this version of the program is exactly the same as we used it, as the one that we used in the previous versions. Let me now go to a prototype application and some benchmarking results. For the benchmarking, we use our supercomputer at the Jülich Supercomputing Center. It's an Atos machine, and we call it a modular supercomputing system because it consists of several modules. So it consists of a module which we call a cluster, and this cluster contains mostly CPUs. We then have a booster to accelerate the calculations, and this booster is a machine which consists mainly of GPUs. And then we have some other modules for the storage and data analytics. And this quantum module I come back to later on. So we then look at the quantum approximate optimization algorithm. which you know is a variational quantum algorithm. It's a hybrid version. It consists of two parts, a quantum part to calculate the energy expectation value of the quantum system. And this calculation relies on an iterative process in which one applies a series of parameterized unitary transformations to the quantum system. And then one has to measure the resulting state and evaluate the energy. And we then also have this classical optimization algorithm, which we carry out on a conventional machine. And this part is used to optimize these parameters, beta and gamma, of the unitary transformation. Now, we used the modular supercomputer architecture to take the GPUs out of it on the booster for the execution of the quantum parts. So these GPUs play then the role of quantum processing units. And this classical optimization part we simulate then on the CPUs of the Jules booster. The problem that we consider is called the simplified tail assignment problem. This is an optimization problem that assigns aircrafts to flights. And the goal is to minimize the overall cost for the aircraft and the flight crew, and this while respecting operational constraints. Of course, we can only consider simplified problem instances. So in this particular case, we looked at instances to find these routes to carry out 472 flights between the airports, with the constraints that routes cannot overlap. And this can be translated in an optimization problem with 40 qubits, which is something which we can simulate on the supercomputer. In principle, we could go to 43 qubits. So here you see some results. The dashed lines are for the quantum approximate optimization algorithm for different cases. So you see the success rate as a function of the number of qubits. For Quaoa, we see that the success rate is not so high. We have a success rate of 1 in 1,000. If we consider the instance with 40 qubits, then for benchmarking, we also looked at two D-wave quantum annealers, the 2000Q with more than 2000 qubits. And here you see the success rate as a function of the relative chain strength. And then we compared it to the newest generation, the D-wave advantage, with the Pegasus architecture for the quantum processor and having more than 5,000 qubits. And then we see that here we have a success rate of about 70%. So just like the previous speaker has indicated, also for this type of problem, the quantum annealer is performing much better than the quantum approximate optimization algorithm carried out on an ideal gate-based quantum computer, namely the one that has been simulated on a supercomputer. So this G version is also a very good benchmarking software for GPU clusters. The reason is that it's memory intensive. So for 40 qubits, we needed 16 terabytes of memory or use it. It's network intensive. And the reason is that if we have these global gates, then we have to transfer half of all the memory. So this means we have to transfer 8 terabytes of memory. And we have a high GPU utilization, so which I have indicated here. So we used up to 2048 GPUs. And yeah, in this case, as I already mentioned, we use the GPUs to simulate universal QPUs. But from these numbers here, you see that it's also a very good test of a GPU cluster. Here you see some weak and strong scaling results. Here on the far left are the weak scaling results. So you can see that if we go from 2 GPUs to 512 GPUs, the compute time is constant, and the MPI time is scaling linearly, so definitely much better than exponential. And then these two figures here on the right show the strong scaling results, one for 34 qubits and one for 40 qubits. So for 34, we used 8 to 256 GPUs, and for the 40 qubit case, 512 to 2048. Again, you see the results for the compute time and the MPI time. And here you see this exponential decrease. So here I come back to the modular supercomputing architecture that we have at our supercomputing center. And what we did now is we used the CPUs and the GPUs of the booster to do this simulation. So the CPU for the optimization part and the CPU for the quantum circuit. What we could do is use the CPUs of the cluster for the classical optimization part of the algorithm, and a QPU to perform the quantum circuit. So, and then I come to this quantum module, which we attached to our modular supercomputer architecture. So let us have a closer look into this quantum module. We have this there to come to seamless quantum computing HPC integration, with the final goal to have quantum classical hybrid computing models. And in order to be able to do this, we have established Jülich, which is Jülich Unified Infrastructure for Quantum Computing. It's a quantum computing user infrastructure for users from science and industry in Europe. In Jülich, we install, operate, and provide access to different types of quantum computers. So we recently installed a D-Wave Advantage quantum system. And to provide this access for the users, we have established a unified portal to provide access to these different types of quantum computers, but also to emulators. So to provide also access to JUGs and to an Atos quantum learning machine. And then for the rest here, we have quantum computers which have different levels of technological maturity. We have experimental ones which are developed in various national and European projects. Of course, we have commercial ones. And here there is a special one. This is called a quantum simulator. And for this one, we have a European project to integrate this quantum simulator in our supercomputing environment. Now, in Jülich, we are not only dealing with the hardware, we also develop algorithms and prototype applications. We provide services and training to our users. We know that this is very important from our very long tradition of providing services and training for our HPC users. And as I said, we are looking into this modular quantum HPC hybrid computing, because in our vision, this is something which is essential to come to real applications for quantum computing. So here, some time scale. So in these periods, we have used all kinds of supercomputers with our Jülich Universal Quantum Computer Simulator to simulate or emulate quantum computing devices. And our plan is to do these simulations on even or on always bigger conventional computers. So the final goal is to perform also these simulations on an exascale machine, which hopefully we can install and operate in Jülich in 2024.